So now I'd like to take a look at a theorem which has a big deal to do with continuity, and that's the intermediate value theorem. Okay, so the intermediate value theorem, or commonly known as IVT, is a very nice theorem in calculus. It's going to seem confusing at first, then really simple, and then really effective. Okay, so let's look at what it says. Let's break it down. If f is continuous on the closed interval AB, so that's the important continuity we need, and k is any number between f of a and f of b, so the values at the endpoints, then there is at least one number, c, in AB such that f of c equals k. So there's I can pick any number between the values at the endpoints, and I'm guaranteed that there's at least one place in x where I get that value of the function. Okay, so let's see it as a picture because that might not be clear. All right, so let's take this here. So here's what we're looking at. Here's f of a. And here is f of b. So f of a and f of b. Basically, we're saying now pick k anywhere between these two values. That means what this function is saying is that if it's continuous between those 2 points, then somewhere I must cross the value k. All right. So imagine if we were trying to defeat this theorem. We would have to be able to make a function so that I can get from here to here without crossing that dotted line. So if it's going to be continuous, I can't do that. All right. I head up. Somewhere I'm going to have to cross. And in this case, that crossing would amount to, there's the c, where f of c is k. The function value at c is k. All right, I can try other ways. All right, so if I tried to avoid it for a while, eventually I would have to do it. So there would be a c. Okay, so I can't get there if the function is continuous. I might even do it multiple times, okay, but still there's at least one. There'll be a C1 there, a C2 there, and another C3. There's 3 places. Now the theorem guarantees that somewhere it'll happen. It can happen more than once. Okay, so let me back up, and I'll just go back to the simple example. Maybe something like that, where there is your c, where f of c is k. But realize, this came from the fact that the f I described here is continuous on AB. All right? And in other words, that ensures that IVT holds and that I can make this conclusion. If I threw out the idea of continuity, then I could start seemingly defeating this theorem, but I'm not really. It's just we're going to see how important continuity is here. So again, if we had this value here, now, if you don't ensure that it has to be continuous, then yeah, certainly I can do this. I could just do something like this. I could just take the function, go like this, stop there, jump up there, and go like that. And just like that, I created a function that does not have a place, c, where f of c is k. Okay? But the problem here is this does not defeat the theorem because f is not continuous on AB. All right? In other words, IVT does not apply. All right, it doesn't apply. And it doesn't apply means it can't say anything about it. All right, it doesn't mean that what you expect to happen doesn't happen. It just means that it's not guaranteed to happen. So this is really a guarantee theorem, because imagine I took a different k. Okay, even though the function is still not continuous on AB, I do have a C value where I take this other K value, but that's just coincidence. It's not guaranteed by the theorem. It just so happened to happen. The theorem says because IVT does not apply, because it's not continuous, I can't make any guarantees. So let's see how this can really be used. And it's actually a very important theorem, despite its simplicity. I mean, what we see is that basically we're just saying that if you have a continuous function, then it has to go continually from one point to the other and pass through all the points, values in between. But where this comes up is in what's known as the bisection method. If we're trying to find zeros of functions, you remember in precalculus or algebra, a lot of times we're asking, when is this function equal to 0? And a lot of times you're doing that by factoring. Now, a lot of functions you can't do that by factoring, and you have to do it by something called the bisection method or more advanced ideas like it. So, the bisection method says, it's for finding zeros of continuous functions. It says, if f is continuous on AB, and either f of a is less than 0, which is less than f of b, in other words, that f of a is negative and f of b is positive, or f of b is less than 0 and 0 is less than f of a, in other words, f of b is negative and f of a is positive. So one value on one end is positive, and one value on the other, and the other value on the other end is the opposite, negative. Then there is a point C in AB such that f of c equals 0, a 0 of the function. So that's what we're looking for. All right, that may sound confusing, but let me try and point it out. Let me take one of the two cases. Let's say here is f of a. It's negative, all right, below the x-axis. And here is f of b. It's positive, okay? So there's f at A, there's f at B. Basically, what this theorem is saying is that if it's negative at A and positive at B, somewhere in between, it will have to cross the axis here. In other words, be a place where f is 0. So, again, same as before. So if we're going to get there, we're going to have to somewhere cross. Maybe it's there, okay? Now, it could be more than once, again, but this is guaranteeing that somewhere it has to happen. So how is this related? Well, basically, this is just IVT, where we've taken the k to always be 0. Okay, and this is the most common use of it, but k doesn't have to be 0. This is just a common use. That's what one place we can use it for. And the idea is that actually, if you want to go a little further with this, is that we could use it to hone down where it is. So, in other words, if we were to have a value there and a value there, and we know that it's positive one place and a negative in another, and we can't see the function because we can't get a graph of it, what we could do is take a halfway in between, bisect the interval, this is why it's called that, and find out what the value is at that place. So if the value halfway between was, let's say, also negative, well, then we know that the 0 has to be somewhere in this interval, because it has to be a place where it's negative one place and positive the other place. And so if we did that again and then took a place in here, found its value, but now we said maybe it's in here, then we know that it has to be, that the value is here. We know it would have to be in this interval here, and we could go further in there, and we could keep bisecting and going closer and closer and find where that, approximately where that 0 is. So that's just a side note of how this is used in computing. All right, so let's look at an example and see how nice this is to apply. Show that there is a root of the equation 4x cubed minus 6x squared minus 3x plus 2 equals 0. So we're not going to do any of the algebraic ways that this could be done, but between x equals 1 and x equals 2. So we're going to do this simply using IVT, the bisection method, the particular version. All right, so we have f of x is 4x cubed minus 6x squared minus 3x plus 2. Which as a polynomial is continuous everywhere, but it's certainly continuous on 1, 2. So let's find out what we get. If I plug in 1, I'll get 4 minus 6 plus 3 minus 2. Oh, I'm sorry. This should be plus 3x. Minus 2. Plus 3x. Minus 2. All right. So I'll get this, and this is going to be negative 1. Then I do it at 2. I'll get 32 minus 24 plus 6 minus 2, and I'll get 12. So it's not really that important the numbers I got, just that negative 1 is less than 0. 12 is greater than 0, so I found 0 was between f of 1 and f of 2. So, since I used a polynomial, well, a function that was continuous on that interval, and I found it was negative one end and positive at the other end, by IVT, there is a c such that f of c equals 0. Oh, I'm sorry, I should have said a c in 1, 2, such that f of c equals 0. So I've shown that there's a 0 or a root of that equation between 1 and 2. And that's how it can be used.